So today we're going to talk about FRP 101, fundamentals of FRP materials and construction methods. So basically the idea of this presentation is to give you all basic information about FRP for those who are not familiar at all with it. It will also help to refresh the memory of those that are not involved with FRP all the times, but will help you with that. So as a general outline for this presentation, we're going to start with what is FRP and the common verbiage that you're going to be hearing in the next couple of days in all these presentations. We're also going to talk about the raw materials that you need in order to fabricate these FRP laminates. And we're going to talk about how to put these materials together when it comes to laminate constructions. And we are going to finalize the presentation by talking about the basic components that you might be facing if you are involved in an FRP piping project. Let's start by answering the question, what is FRP? FRP is pretty much a liquid resin that impregnates glass reinforcement and you let it cure to produce a part. FRP actually stands for fiberglass reinforced plastic, but you can also hear terms like GRP, which is glass fiber reinforced plastic, RTP, reinforced thermoset plastic, or just simple fiberglass. GRP is a common name that you will hear a lot in Europe. You might ask yourself the same question, why using FRP in your project? Well, basically for two primary reasons. Corrosion resistance and cost. So essentially, the material selection for your pipe or tank will be dependent on the service fluid and the cost associated to your project. FRP is widely used in highly corrosive surfaces due to its high corrosion resistance properties and lower cost compared to their metallic counterparts like special alloys. When we talk about the raw materials that we're going to use for FRP, there are two primary constituents, the resin and the glass. The resin is the thermoset polymer that will give the corrosion resistance and the temperature resistance property to your laminate. The glass in that combination will give you the strength and stiffness for your laminate. So when these two materials are separated, resin by itself is weak and brittle, and glass is only strong on tension. So when you combine these two materials, you get a strong and stiff part because the resin will bind those fibers together. So a common example that we all probably are familiar with in a construction application will be concrete and rebar. Since the resin will be the corrosion resistant part of your laminate and the temperature resistant one, so it's important to talk about the resin selections and why you need to select the proper resin for your system. So here I have a list of the most common type of thermosetting resins for industrial use. We can see we have vinyl ester, polyesters, and epoxies. And the factors determining the selection of these resins depends on the chemical exposure, temperature rating, flame spread rating, and life expectancy. Now, it is very important that you understand your service in all the elements that you have in that fluid, like trace elements. All these factors will determine the lifespan of your equipment. So it's very important that you understand that. What happens if you do your homework and then you realize that a thermosetting resin is not enough corrosion resistant for your component? Well, then let me introduce you to dual laminates. Now, I'm not going to go in too much in depth about dual laminates because it's 101 FRP, so I'm going to focus my presentation on FRP. But I just wanted to mention that there is another option, is a thermosetting resin is not enough, which is thermoplastic material. And Michael Krause is going to talk about thermoplastics more in depth. But for now, the idea of this application on FRP is a dual laminate. And it's called dual laminate because the thermoplastic material will be the liner in contact with that surface. And then the armoring or the strength of that application, either a tank or a pipe, will be done by the FRP around it. This type of application needs special attention at the time of fabrication because they're very complex and needs further steps in order to achieve good quality. So now that we talk about the resins, the corrosion resistant part of it, let's talk about the glass reinforcements. And here in this slide, I have all the common type of reinforcement or glass reinforcement that you will see around the industry. We can see we have single end roving, multi-end roving, surfacing veils, woven rovings, chop strand mat, and directional rovings. So let's go in depth in each one of them. Let's start with surfacing veils. So the reason why it's a surfacing veil is because it's the first contact layer of glass reinforcement in contact with your fluid. There's multiple reasons because of that, and one of them is because it can hold all can hold 90% of its weight in resin. And we already know that resin is the most corrosion resistant part of your laminate, so that's the reason why. We have different type of veils like C veils, ECR veils, Nexus and carbon veils. And we have a table here explaining the strength and weaknesses of each of them. C veils and ECR veils are very similar. The strength about these materials or these glass reinforcement is that they're very good corrosion resistance to most acidic chemistries, and they can easily be applied in multiple layers. Now, there is a weakness about these two type of veils, is that they are not good in most basic chemistries, such as salt solutions. Then we also have a Nexus veil, which is also called a synthetic veil. These are very good corrosion resistance to sodium hypochlorite, oxidizing agents, and most base chemistries. The problem with these is they're not good in acidic surfaces. We also have carbon veils. They're good heat resistance and static charge dissipation and very good for HCl services. The problem is they're costly and they can be difficult to fabricate with because of the stiffness of that laminate. And we have specialty veils like Halar, Kanar, or nylon. They're good in abrasion resistance and very good flame spread properties. Weaknesses, very costly, and because of the same thing, some fabricators doesn't have too much experience using these type of veils. Let's move on to the next type of glass reinforcements. This is the chop strand mat, or commonly named mat. This type of reinforcement consists on randomly oriented fibers. Now, these fibers are randomly oriented on the plane and will give you multi-directional properties or multi-directional strength. Now, it's not a very strong type of laminate because of the same randomness of the fibers. So we use these mainly as bedding, and when we say bedding, is to build up thickness on our laminate. It can hold between 25 and 30% glass percent when saturated with resin. So you can see it's not as corrosion resistant as the surfacing veil, but still can hold some corrosion resistant due to the glass percentage and the resin percentage on it. It can be applied on a roll, or it can be applied with a spray chopper gun. And I'm gonna go in depth about the spray chopper gun a little bit later. Let's move on to the next type of glass reinforcement, which is the woven roving. Now here we're starting to talk about the first structural or structurally oriented glass reinforcements. And woven roving, or just called woven too, it's glass reinforcement that the fibers are weaved in a 0 to 90 orientation. So it's providing quasi-isometric properties to this type of glass reinforcement. Now, as you can see, the glass content is between 55 to 60%. It's higher than the chop strand mat and way higher than the surfacing veil. And for that reason, we use this type of laminate just for structural strength and for the structure of the laminate. The next one is glass reinforcement, continuous rowing for multi-end for chopper gun application. So this consists on a strand of continuous fiber on a roll that is connected to a chopper gun. Now this chopper gun will spray and cut these fibers onto the surface you're laminating into. It's pretty similar to the chop strand mat with the oriented fibers, but it's applied directly to your application. So it can be done manually, like the picture in the middle, or it can be done automated by a machine. We definitely prefer the automated process due to the consistency in thicknesses when you're applying this type of reinforcement. Because if you do it manually, how sure are you that the thickness will be continuous around the whole part when a person is doing requires a lot of skill to do that. The other type of continuous drawing that we have is the single end filament winding. So this one is not going to be cut. It's still the same strand of fiber, and it's going to be wind around a mandrel, either axially, in the hoop direction when it comes to the fabrication of tanks, or horizontally, and we're going to talk about a little bit more about that. This produces the higher glass percentage on laminates, and it's very strong. We also have unidirectional rovings and multi-directional rovings. Unidirectional rovings are just fibers oriented in one direction, and that direction that the fiber is oriented is going to give you the strength of that laminate. Multi-directional rovings are similar to the woven rovings, but in this case, they're not 0 to 90. They have a specified angle of orientation and will give you the properties in those angles that you require the laminate to. All right, so we already talked about the resins, corrosion selection of the laminate. We talked about the glass, the strength of that laminate. Now let's talk about how do we put this together on a laminate. So here, what I have is a cross-sectional view of an FRP laminate. We can see that in the left, we have the process fluid. So the orange and yellow side of my laminate, it's what it's going to be called the corrosion barrier. The reason for that name is because it's the most resin-rich part of my laminate, because I have my surfacing belt as the first layer against that process fluid to prevent corrosion in my laminate, followed by my chop strand mat. So chop strand mat, in this case, what it's doing is building up the thickness that I need for that corrosion barrier, which can vary depending on your service, the type of resin you're using, temperatures. It can go up from 100 mils to half an inch, depending what you need for your service. On the blue stripes will be the section of my structural layer. So this section will give me the strength of my laminate. We have the corrosion resistance on the left, the structural side on the right, and that structural side is usually divided by something called bedding, which is done by the chop strand mat or the mat. And the structural side of it can be done either by the same mat, more thickness applied to it, can be done by woven rovings, unidirectional fibers, or filament winding. Whatever type of glass reinforcement you're trying to use for your application will give you different properties for that equipment. If your equipment is located outside, exposed to the UV rays, so we can also have UV resistant coating as required as the last layer of your equipment. Now that we know, now that we talk about resins, we talk about glass reinforcements, let's talk about how do we put all these materials together with the different manufacturing process that we have available in the industry. As a list, we have filament winding, hand layup, pultrusion, vacuum infusion, compression molding, and centrifugal casting. Let's start discussing what is filament winding. So filament winding consists of these continuous strands of glass going through a resin bath and then winding around a rotating mandrel. As you can see in the picture, the carriage is moving laterally across that mandrel and the mandrel is spinning. Here, I can show you a video of that process. So filament winding can be called winding, helical winding, or type 3, or even type X. So when you hear these terms, it's, I think it's a video. Yeah, the video was, yeah. All right. So well, that was the process of filament winding. We have different type of filament windings, as you can see, especially depending on the orientation on that strand of of fiber. So 55-degree helical winding is mostly used for manufacturing of piping because the 55-degree will give you 2-to-1 properties against axial and hoop. You can also have a custom angle on your fabrication of filament winding, which will alter the properties on that, the axial to hoop properties on that application, but it's something you might need to do or you might want to do if you want to, for instance, increase the axial strength, if you want to increase the spans of your supports, or if you have a very unique application that requires the changing on that angle. Hoop uni, it's mainly used for the fabrication of tanks. So here, the angle of winding, it's around the 90-degree in the horizontal, and will give you a lot of hoop properties or hoop strength in that tank. Now, this is usually paired with unidirectional fibers going in the actual direction to give you the strength in the actually direction of that tank. The next fabrication process that is very common, it's probably one of the most common ones, it's hand layup, or also called contact molding. So it consists on just manually applying the laminates of on a surface, on a mold, pouring the resin or pre-saturating the laminates also too, and then using a roller to extract as much air as possible from that laminate. This type of process is also used when the geometry of your part that you're trying to build, it will be hard done by filament winding. So when the geometry of that part gets too complicated, then contact molded or hand layout might be the solution for your problems. As you can see here in the picture on the right, they're manufacturing a flange manually, and you can see that the guy in the middle is doing with their hands winding the mandrel for that piping. There's two types of hand layup. We have type 1 and type 2. The difference between these two types is the type of glass reinforcement you're using. So for type 1, everything on that laminate will be chopped strand mat. Type 2, though, it's alternating chopped strand mat with woven roving. And because of the addition of woven roving, you're increasing the strength of that on that laminate. Now, type 1 is mainly used for small components, small piping sizes, because it's easier to mold around a small diameter. Here in the picture on the left, you can see they're doing type 2 on a top head for tank. Pultrusion. Pultrusion is another fabrication method mainly used for structural beams or FRP structural beams because it's repeatable and it's done. I have a picture here. The process pretty much consists on layers of or strands of fiber going through a resin bath and then being extruded through a die. The problem with this type of beams is that in order to extrude those fibers and the resin through the die, they need a wax as a mold release. And that will reduce the bonding properties to other FRP equipment. So if you want to do a joint by using FRP, that will reduce the bond strength on that part. So that's why we recommend to always bolt these to whatever equipment you're trying to attach it. Vacuum infusion is another fabrication method. This type of fabrication produces very strong parts, but the problem is that the glass reinforcement based on the same nature of how you fabricate it is very high, so it's not very corrosion resistant. And another type of fabrication methods are compression molding and centrifugal casting, and you can fabricate more specialized components like flanges or specialty piping in this type of manufacturing process. Now, let's move on to all the main components that you might be facing and what's available for you out there if you get involved into an FRP piping project. As a brief list that I have here, we have flanges, elbows, T's, and joints, among others, but those are the most basic ones that I thought it will be important to talk about. So let's start with flanges. Flanges, we have mainly two types. We have the full face and the lap joint or Van Stone flange on the right. So the full face, it's a regular flange that is connected to each other, full face. The bolts are going through the whole flange. And then we have the lap joint or Van Stone flanges with the stop of the flange is a little bit smaller. And then you have backing rings where you have the bolt patterns to attach it. Flanges are quick to install to put piping together. But the problem with flanges is also there are potential leaks for your system. So it's a trade-off between a quick installation for your piping or having the risk of having leaks. Let's talk about elbows now. There are mainly two types of elbows, two on FRP. You have smooth radius that can be either short or long radius, like we normally have on steel piping. And we also have miter elbows. So miter elbows are mainly used for big diameter piping. When contact molding for this huge pipe, fabricating an elbow on will be hard to do, so they pretty much wind these straight sections of pipe and then they cut it into an angle and put it together to fabricate an elbow. Like I said, mainly used on big diameter ducting and piping. We also have the tees. Now there are two types of tees that you might face in your project. You have fabricated tees and integrally molded tees. So let's start talking about the fabricated tees. The picture on the left pretty much consists on a straight run or a main run of pipe when you will drill a hole and connect a nozzle to it. You can either weld it outside or inside and outside depending on the pipe diameter. And you have the integrally molded tees, which are, as the name says, molded or laminated on a mold integrally, and they can be either filament wound or they can be hand laid up on that mold. And our last important component that I wanted to talk to you about are the joints. We already talked about the flanges. We know that the flanges are quick. They are not the cheapest way also to connect piping, but you have uh, another type of joints like socket adhesive glue joints, the picture on the left. So pretty much consists on having two ends of pipe. One will be tapered down on an angle. The other side of the pipe will be tapered on the opposite angle, and then they're going to be self-aligned, and glue will be applied to that joint. Um, Weaknesses about this type of joints, they're not very good in bending, and the quality of the joint will be very skill dependent on the people doing the grinding and doing the application of that glue. You have O-ring and bell spigot. That's the other type of joint. Very similar to the socket adhesive joint, but in this case, you're doing O-rings to connect that pipe together. Now, there's a problem with this one that you will need axial restraints because of pressure thrust on that piping. So it's mainly used for buried applications. You also have button strap, or commonly named butt wrap or butt joint. This type of joint is the most strongest one. It's the most costly one too, at the same time, very labor intensive. But the idea of this is just putting two pipes together, two plain cuts, put it together and wrap around it. It's what we call a hard weld. And I do wanted to finalize my presentation just by saying that there is literature out there. We have ASME RTP1, latest version, it was 2021. It's a standard that we have been working on for a long time now. And it's mainly used for the fabrication of tanks and vessels. You also have help with ASME Section 10. And for piping, we have ASME NM2, the latest version is 2022. So this is the literature out there that you might find helpful if you're involved in an FRP project.